Okay, again, welcome to Physics 4B. Today's focus is on the electric potential. There was an assignment that is actually you're supposed to have done. I know I gave you toward the end of the week because of the fact that some of you are not going to be alive in here necessarily. And that has to do with the something that you should have seen way back when you did Physics 4A. And that is the potential energy, the kinetic energy, the total mechanical energy, and for basically conservative and non-conservative systems that you would have done in Physics 4A. And basically, at that point, when you reach the work energy theorem, there is a one-to-one correspondence between the work energy theorem and F equals to ma, and Newton's laws, if you wish. Okay, so that is basically the correspondence between the work energy theorem is as powerful and as useful as Newton's laws. In other words, one could have done the following: forget about Newton's laws of motion for Physics 4A. We're going to start with the work energy theorem and assume it's kind of a postulate. And then from it, we will derive Newton's laws of motion. So we could have done that in Physics 4A. But of course, traditionally, Newton's laws of motion were first discovered, and then we arrived to the concept of the work energy theorem. In the discussion before we even started the class, I asked you guys one of the questions is basically, okay, we did Newton's laws. We think that with Newton's laws, we can solve anything. So why in the world do we pass chapter or whatever that is, 5 or 6 or 4, I think, in the book? And the answer to it in a nutshell is one of the questions that we would ask, for example, once we reach the concept of the energy is yes. We grant Newton's laws of motion. Let me show you a screen to illustrate this thing in here. Granted that Newton's laws of motion are valid. In other words, that is by hypothesis, if you wish. Newton's laws are correct, okay? And if I have an object, okay, that was initially in its initial state at some point in space, so it's characterized by position in space. I'm going to call it R because that's what we use for the position of objects. At that point, I have the object position, but I really don't have a full description of its state of motion. I need its velocity also, V1. So the object now is well defined in its initial state. Then we apply F, a force on it. And let the force do what it does. The force, of course, will change its motion and do all of the magic that it's supposed to do and all of these things. And then come later on in the future and find the object somewhere in a new location, characterized by the position vector R2, and with a new velocity V2. Okay? Now, after we do those two observations, basically, we have an object initially at some position with some initial velocity and wait a little later after the force does what it does and then find it in a new location with a new velocity. Hey, we ask the following question. How did the force do its trick? How did the force do it? Basically, that's the question that we want to, it's kind of curious trying to find out. Yes, we know between two instants, F equals to ma. That's true. Between consecutive instants, that's true. But what happened to the big scale? Well, it turns out, according to the work energy theorem, after the object passes through a certain path, that this force actually will do work. And that work will be exactly equal to the change in a quantity that we're going to define very quickly, Ke, or kinetic energy, yes. And that value has to do also with the initial state and the final state. Remember, the initial state has an initial value for velocity vector V1. So we're going to define the initial kinetic energy as simply equal to 1/2 of mv1 squared. So that is actually state variable. That is actually defined by that specific location and that specific velocity, namely that state of motion initially. In the final state, we have a new kinetic energy, which is Ek2. So those are two end values, the initial and the final kinetic energies, and between them, what the force does, actually, it does work. So that was a question to go beyond F equals to ma, and that is to ask, to ask what is the secret? How does the force do it? Well, the answer to that is the following. The answer does work in such a way that that work is the change in the kinetic energy of the object. So that's basically one way of getting to pass chapter 5, so to answer this question. And as I said in the beginning, the work energy theorem, which is this one, is as fundamental as and is equivalent to this statement, F equals to ma. Those are two statements that are equivalent. You can go from, actually we derive this one from F equals to ma, and we can derive F equals to ma from this one. So basically this is equivalent to Newton's laws of motion. So that is really one of the things that you have done in physics 4A. Now, past that one, it turns out, by definition actually, because we have to define these quantities in order to arrive this expression, that the work depends on the path. It's equal to the integral from the initial position R1 to the final position R2, in this case, of this force times displacement. Again, this is just a review from way back. This is the dot product. This is the first vector times the second vector times the cosine of the angle that is between them. So if they make a 90-degree angle, that force does no work, okay? So that is basically how we define the work in this case. It would be nice if somehow, I'm trying to give a summary of what you did in physics 4A, it would be nice if we can find the antiderivative of this function. And that is a big if. It's not granted that it's true, that this antiderivative exists. If it does exist, then we can express this integral or the work in terms of that antiderivative. The only trouble with it is we usually don't express this thing with the antiderivative, we express it with the negative of the antiderivative. Because if we're just concerned about the antiderivative by itself, we will find at the end the total energy is equal to, basically, we will have to define the total energy of the system, mechanical energy that is, as is the kinetic energy minus the antiderivative, which I'm going to call G in here. So this is my antiderivative. But that's not really cosmetically beautiful. So when physicists reached this point, so instead of using G in here, they used U, with U being defined as negative of G. So they have, so which means a minus times minus becomes a plus, and the kinetic energy is properly defined as kinetic energy plus potential energy. So the potential energy is actually the negative of the antiderivative of the force function, basically. But that is if the antiderivative exists. If the antiderivative doesn't exist, then it cannot define the total mechanical energy in this case. So the universe then is divided into two kinds of forces. These are two forces. Forces that I can find the antiderivative, hence the potential energy, and the potential energy in this case is related. I'm going to take the one-dimensional case and immediately we're going to go to the 3D. In the one-dimensional case, the force is simply equals to minus the derivative of this potential with respect to x. So I can find that. So remember, the minus was introduced just for cosmetic reasons so that things look symmetrical, that's all, okay? And forces that I can't do that, there is no U, doesn't exist. So these are the so-called conservative forces. And this is our non-conservative forces. In other words, I can always go back to my integral for the work and find that if I have really an antiderivative, that this is just the difference between the final value minus the initial value, regardless of which path I go through. If the particle went through this path or went through another path like this one or straight line, it doesn't matter. The difference between them is just the difference between the potential energy. So if the particle rose from one point to the other, it doesn't matter which you go on the incline. You go straight out, or you go up, or you go at an angle, or you go around the universe and come back. It's just a difference between the two heights. That's what matters in the case of the potential energy. Same thing for the spring. It's 1/2 of kx squared. The same thing, it doesn't matter. It's only what matters is the initial and the final stretching of the string. That is the difference in the spring, I'm sorry. That is the difference in the potential energy in the case of the spring. So those are two examples, as a matter of fact, of conservative forces, namely the force of gravity and the force of a spring. This is the things you did in physics 1A, 4A, I'm sorry. In non-conservative forces, such as friction, for example, it matters which path you went through. If you went straight out, you're going to lose energy in this case just from going from one end to the other. But if you went around the corner and came back, you're going to lose energy throughout the entire path. So friction, for example, is non-conservative energy. In other words, friction, you cannot find this antiderivative for it. As a matter of fact, friction depends on velocity. So this integral doesn't exist because this depends on velocity, the function depends on velocity, and the integral, so it's going to be complicated. It's not going to exist. This integral doesn't exist for friction. So that's an example. The other example, of course, if you have an engine, for example, pumping energy into the system, non-mechanical system, non-mechanical source of energy, such as chemical energy. So, for example, in this case, the engine, okay? The car engine, that's what I mean, a motor, okay, adding energy to the system. So those are two examples from each of the two kinds of forces. Whereas non-conservative forces don't exist, then in this case, the total energy is conserved. E final is equal to initial. So that's basically what we have seen in physics 4a. If there are non-conservative forces, then the difference in the total energy, gain or loss, is equal to the work of the non-conservative forces. So for example, if I have friction involved, there is friction drains from my system energy constantly. So the final mechanical energy is less than the initial kinetic energy, and the difference is the work done by the friction, okay, to overcome the friction. Or for example, if I have a system that is being pumped into by an external agent energy, for example, a motor putting more and more energy, for example, car was stationary, now it's moving. So where did it get that energy from? It's from the engine, external source, in this case, a non-conservative force again. So the point being in here is this is basically what you have seen. What is interesting in here is, can we, that is the question for chapter 23, can we classify Coulomb's force, basically the one that we discussed chapter 21, hence the electric field, to also derive from potential? That is the question, okay? Can this force also be written in this format? That's really the question that we need to answer, okay? So if it is, then we should be able to define the potential, okay? There is a big mathematical, actually, if we were in class, we would have played a game to define a force randomly, and we find that any force other than 1D, any random force is non-conservative, except special forces. And Coulomb's force is actually not in 1D, it's in 3D. Same thing with the force of gravity, actually it's 3D, only it appears to us to be 1D when we are on the ground because we're considering only the height. So the force of gravity actually is three-dimensional force in a sense that exists in all 3Ds. And these two forces, even in the 3D, in the case of the force of gravity, derives of potential. So it's not granted that any force, even in the absence of friction, and even in the absence of an engine, higher dimensional forces more than 1D, they are going to go by themselves. I mean, random force is going to be non-conservative regardless. Okay, so that's one of the things. I mean, it's a mathematical problem. Actually, it's not physics at all, but that's the challenge with it. But nature was kind enough for us that it provided basically for physical systems all the forces that we deal with are conservative forces. And that is what we're going to do in chapter 23 to show that actually the force of gravity in this case, I mean the force of Coulomb in this case, is a conservative force. It derives of a potential. There is a theorem, like I said, in math, in calculus, actually, on how to find the force, to show that the force derives of a potential that involves the so-called cross derivatives and all of that. And that is actually fine. And you can prove that the force derives of a potential. But it's still, you need to ask the question, what is that potential? So you need to find the potential, which is not always easy. But it would be easier actually, to answer the question, does the force derive from a potential? If you actually find the potential itself. And that's what we're going to do here. So we're not going to show that the electrical potential, the electrical field derives of a potential, or the electrostatic force derives of a potential. We're going to actually find the electrostatic potential. So once we find it, then that's it. That's the answer to the question. We don't need to prove that it derives from potential because we already know. We have found the potential. So this is in a nutshell the entire chapter basically of how it really shapes up. Okay, this is connecting way back to when you guys were in physics 4a and bringing that concept to this point in here. The only caveat And I'm going to ask this question. How many of you, at least basically, have taken already Calc 3? If you did, I need to know in here. If you already did Calc 3, okay, 1. Anybody else?
I did.
Okay, 2. If you did, 3, 4. Okay, good. 5. So we have a good number. Okay. If you did, this should not be too foreign to you. Okay. If you did not, chances are you're going to see it toward the end or the middle of the Calc 3, okay? That is multivariable functions, basically, functions that are more of what is actually day-to-day business. And when we first see the symbol for the derivative, for example, in multi-derivative functions, it looks kind of odd. It looks like kind of a, hey, what is that looking curvy thing, okay? And it's kind of an alarming thing. My thinking for you guys is you should not be stuck with the symbolism. You should really be more toward basically, how do I do it? Okay, show me how we can calculate this thing. That's one thing. The other thing is, and even the calc teachers will tell you that, hey, you think that this is odd. Actually, the other one should be the one odd. Almost any function in nature is a multivariable function. So you have been basically, if you wish, handled with care from the days when you were in high school, when you first learned about functions, up to this point, that functions are actually single variable. But that is not true. That is actually the exception. If you see a function that is a single variable, that is when your all of the bells and all of the alarms should go on, because of the fact that is an odd thing. The odd thing is a single variable function, the one that you've been dealing with up to this point, okay? And I know in physics, that's what we do. And that's actually the ultimate goal too. And even in this chapter itself, although the definitions will be for multivariable functions, in physics, what we do, we eliminate all of the other things and we make the problem as simple as possible so that we can handle it. Even in this case, when we introduce the gradient, which is the operator that takes derivatives of multivariable functions, we're going to actually resolve it to a single variable. We're going to go back to a single variable by using symmetry, for example, by using other arguments and say, the only thing that changes in this problem is actually this dimension. So all of those partial derivatives that we're dealing with, they're actually single derivative, okay? So that is really the contention, if you wish, that some of my physics 2 students come to this point when we get into the potential, where we are really have to introduce those symbols. But my thinking is, and hopefully you guys will be with me, is that don't be stuck on the symbols. And we're going to resolve those symbols at least until chapter 30. After that, things cannot be undone. You have to go into multivariables once we're dealing with Maxwell's equations, we're trying to solve them, because there is no way of undoing them at that point. So toward the end, I'm hoping by then that you would have learned enough stuff in calculus to be able to work the algebra that is coming from Maxwell's equations. Does this make sense to you guys a little bit? Do you see it?
Yeah, that's it.
Okay. Okay, I did an activity, I guess, hopefully guys you will go through it when you start this model. Actually, it was a required step for this model. I hardly do that. I always give freedom for my students to move through model basically from the top to bottom if they think they're done with it. But this, I made it special so that you cannot actually move past this point on the model unless you finish that activity. And basically 2 kinds of multivariable functions, you're supposed to find their respective derivatives and they're actually with respect to x and y. Another word of caution that I'm going to put in here before we proceed. All of these multivariable functions are actually 3 dimensions. They're in the x, y, and z in the Cartesian coordinate systems. In the non-Cartesian coordinate system, they have the corresponding variables for them. What we're going to do, actually, we're going to stick only with the 2-dimensional representation of that, the x and y, because it only introduces a complication. The minute we get into other stuff later on, then we will be forced to get into the 3D. So at this point, we're going to, all of the examples and the symbols and everything, there will be 2Ds, but so don't lose don't lose the fact that actually they are supposed to have a z variable in them too. Okay, so that's another word of caution that I'm going to approach this one. So this is in a nutshell basically how that introduction was. So, and I'm not sure if I should go through that examples because it's left as an assignment for you guys, or maybe make a new one, okay? Because you can make whatever you like, okay? So one of the function was x squared square root of y. And the other one, I mean, that's actually the example. So let's do the example and then take it from there, because it's important that we need to handle the algebra before we proceed. So, because I don't want the example itself to be not clear too. So basically, the example gave you an x squared square root of y, and we want to find the derivative of this function now, because this function is dependent on two variables. The thinking is, now how am I going to find these derivatives? Okay, I'm not going to go through the definition of the derivative, which you have seen probably the first time you have seen the derivative, and it still holds the same true. Add an h to the variable with respect to which you're deriving, and divide x plus h, basically f of x plus h minus f of x, divided by f of, or divided by h, I'm sorry, and take the limit when h goes to 0, and that is your derivative, okay? So that is basically, it still holds true in here, except that you have to be specific. Are you doing it with respect to y, or are you doing it with respect to x? And the point is, at this point, we're gonna go and use the algebra, basically. So, this is the symbol for the partial, okay? So we're doing it with respect to x in here. So what we're saying in here is, y is constant at this point. That's what this curly thing in here is. The minute you look at the denominator, you're saying the other variable must be constant. I don't care for it. I only care for the variable with respect to which x. So treat y as a constant, so square root of y is square root of y. Think of y as being 10, for example. Square root of 10 is square root of 10. And now I have to take the derivative of x squared, which is, according to the algebra, is, the derivative of x squared is, this is derivative 101. Anybody? Okay, I'm not seeing the sharing things. 2x, very good. So yeah, that's really what it should be. So it's not hard to think that it's 2x then times the derivative of, times the square root of y. Okay, now let's do the other one with respect to y now. So if we say what is the derivative of x with respect to y, then x is constant, which means x squared is constant. So if x is 10, 10 times 10 is 100, so that's going to stay itself. So this is not going to change. Now, okay, I'm probably not sharing the screen, am I?
No.
I'm sorry. So here is the derivative, okay? So again, x squared is constant, so square root of y is the one that I have to find its derivative. Again, what is square root of, what is the derivative of the square root? Square root of anything with respect to that thing. Any idea? Okay. Again, 1 over square root of, or 1 times, 1/2 times square root of to the power negative 1/2, or y to the power negative. So it's all the symbols again. So if you're asked to do something like, for example, on Canvas, and you would want to express mathematical expressions, the way that you guys doing them right now is fine. Okay. So again, so it's the 2 in the denominator times square root of y. Again, at this point, we're treating y is the variable. Here is another thing that I want you to do, okay, and it's not in the practice. What is the derivative of this derivative with respect to y? So here is the question, and you can probably look at it now before I move out. So I want to take the derivative of, with respect to y, of the derivative of the function with respect to x. This is the mixed derivative. This you will not see in the single variable functions. The reason why I'm saying this is probably a good place for it now is because down the road we will come to hit this mixed derivative and we will come up with some interesting properties. But I want to discover it right now. This used to be part of a homework assignment, by the way. So it's 2x square root of y So the derivative with respect to y of the derivative of the function with respect to x. Remember, the derivative of the function with respect to x is 2x square root of y. Okay, so somebody already, okay, let me stop sharing the screen. Okay, so it's gonna be x over square root of, so yes, correct, okay? So now, you're right, okay? So now we have this function that we want to take its derivative not with respect to x, but with respect to y. So 2x stays itself, okay? So 2x stays 2x times the square root of y, the derivative of square root of y, again, is going to bring a 2 square root of y, and the answer, of course, is x over square root of y. Now, if I do the same thing of this function now, the derivative with respect to x of the derivative with respect to y. So the order now, I'm keeping them mixed. So the order is not the same. So I'm taking first the derivative with respect to y, and then taking the derivative with respect to x. So, I'm sorry. And then taking the derivative with respect to x. So the answer, again, I have x in here, squared, which if I take its derivative is going to be 2x divided by 2 square root of y, and the answer is the same. That is the point I'm trying to argue in here, that mixed derivatives are the same. It doesn't matter which order you do. Again, if you're a math person and you have taken some higher algebra and arguments, you will find an argument why this may not work at some exception. Those exceptions don't exist in physics. Mixed derivatives of functions like this one always are the same. So it doesn't matter which order you do. You take the derivative with respect to x, and then you take the derivative with respect to y, or you take the derivative with respect to y and the derivative with respect to x. The mixed derivatives are the same. Okay, as long as you same dimensions of these derivatives. Okay, so that is only a point that I want to take in here. And if enough exercise of these things, unless you guys have questions, I trust that you guys, at least the ones who did not do Calc 3 yet, did not finish it yet, that you should not have difficulty with this, the examples that I have. All you have to do is consider the other variable constants. Okay. Yes. If you have difficulty with it, please do not hesitate. For those who are taking Calc 3 now, this is the time when you actually have to handle this one. It's going to be part of exams where you're going to be given potential, you're going to find electrical field for it, and vice versa. So you need to have practice with that. So you need to really, it's part of homework assignments too. So you really need to have full control over these things. Most of the times it's an easy derivative, it's an easy integral, but you're going you have to have mastery of these skills in here at this point. Come down road, when you are in Calc 3, you will have far more complicated situations to deal with, but we don't care for those. By then, the basic things you should have handled them. Is this understood? Can I get thumbs up for this one? That this is basically the strategy. So I don't want you guys to feel like this is overwhelming and you cannot do these things. I want you to be at ease with it in taking these simple derivatives. Come homework time or exam time, you should be ready for it, okay? If I get that from you guys, then I'm going to move on. Now we're going to define the work in general and basically have the definition of the potential for this thing in here. So the work then is force times displacement, but actually it's a vector force, as I mentioned before. So this is the work for a force integrated. This is sometimes in the book, I think it refers to DL, DL being the displacement in here, because R has a specific meaning, and I think I agree with that. R has a specific meaning, and that is the radial distance. It could end up being the same thing, but DL is a displacement in general. So I have between 2 points, point 1 and point 2. This is the work that a force does between 2 points, okay? Here is the situation that we're going to start with. I have a point charge, which I'm going to call Q, okay? sitting by itself and minding its own business, creating its own electric field that I know is radial. So the electric field for this charge from chapters before actually, it's 1 over 4 pi epsilon naught times q divided by r squared in the radial direction. So that we know, okay? Here is the thing. We're going to bring a charge from infinity. Remember, this force drop, the electric field drops like 1 over distance squared. And the force then, which we know, if I bring a charge which is a unit charge or even a non-unit charge, Q naught, that Q naught is going to be subject to this force. So I'm going to bring charge from infinity. At infinity, the electric field is 0. Therefore, the force is 0. Because when R is so big, 1 over distance squared is negligible. So a charge sitting at infinity has 0 charge, 0 force. I mean, it's subject to 0 force. So I'm going to bring the charge from infinity and put it at a distance R. So this is my Q naught. So it traveled from infinity and it reached the distance R, described by the unit vector R. At that point, I want to hold it there. Okay? But remember, usually I take charges to have to be of the same sign. So I really have to fight this electrostatic force when I'm doing that. Do you guys understand? So, because these two charges are repelling by themselves. I mean, yes, at infinity, there is no interaction. I don't worry about it. But as I bring it closer and closer, the repulsive force now should make it so that I have to actually do work to bring them closer. Do you guys understand that? I have to actually expend work. If somebody tells me, okay, how about if Q naught is not positive? How about if it's negative? Well, if I let go of it from infinity, it's going to do work for me then. Okay? By accelerating, by getting kinetic energy. So at some point, I will bring it in here. Then at that point, if I want to hold it in that place, I really have to spend energy at that point to hold it there. You guys understand that? I have to do work, and I'm going to take them both positive in this case to make the concept a little bit easier, to assemble these two charges. So in order to assemble the two charges, I need to expend work. We need work, okay? So the question is, how much work do we need to spend? That is a question. And the work actually is defined up there. That's a force times displacement, that's all, okay? So that's what I need to do. I know the initial position, which is at infinity, and I know the final position is at a point R, so all I have to do is find this work, do the integral basically, that's it. So, the work then done, if I can turn on this thing, the work then done, is everybody following me the argument now, the physics argument, forget about the math, okay, because we're gonna go to the math now. That basically I have charge sitting by itself. I know from the previous chapters how much electric field it creates. I know how much actually force is going to exert on a charge, okay, sitting at any distance. It doesn't matter what that distance is. And if I bring it closer, I know exactly how much force it's going to interact. Now I want to know how much work I actually have to do in order to bring this charge to that point, because I have to overcome this electrostatic force to do that, to assemble these two charges and put them near one another, okay? So that is the challenge. So I'm going to plug in the value of the force, which is 1 over 4 pi epsilon naught times the charges, actually, Q1 times, Q naught times Q. The integral is between infinity and R, okay? Of the force, and the force is actually 1 over distance squared times r hat times the displacement. Okay. Here is where that dot product has to be fixed. Okay. I'm going to redraw the picture again. So I have my initial charge Q. I have my charge in here that is traveling to a final position. This is the final position R. At some point, it's at this distance, okay? So this is the R. This is where the electric field that I computed with R, and this is where R hat is. R hat always points away from the charge. but the displacement is coming from infinity to that position. So my displacement actually has a negative sign. So my displacement dr is this way, or dl, I'm sorry, is this way. Okay. So r hat and dl, which is actually dr in this case because it's a radial displacement. So this is actually a dr also, it's a radial displacement, but it's in the opposite direction. So it should be minus dr. Because the unit vector has a length of... Okay, no problem. So this is the work, okay? The work is force times displacement. The only thing I have to be careful with is that the displacement is in the radial direction. I'm bringing the charge from infinity on the same axis, okay? On the radial direction. So the displacement is, in this case, the infinitary displacement dl is actually the change in the radius. But the change in the radius is coming from infinity toward where the charge is, towards closer from the charge. So in this case, dl is dr, but both r hat, which is pointing this way. So this is my r hat. It points radially. It's a unit vector in the radial direction, but the displacement is coming this way. So this is my dr, if you wish, which is a displacement coming on the radial direction. Both of them are in opposite signs. Does this make sense? So I have to be careful with this dot product in here, and because r hat is unit vector, so its length is 1. The length of dl is actually the displacement in the radial direction, which is dr, and they make an 180 degree between them, so it's a cosine of 180 degrees, which is -1. Does this make sense, that this dot product resolves to this number? Yes? Because the vector E, which is the electrostatic field, is pointing in the radial direction. So it has times r hat. The displacement is coming from infinity toward the position closer from the charge, and it's coming through the radial direction also. And it's in increments of dr2, but it's in opposite direction. So the cosine of this 2 will give me a -1, cosine of 180 degrees. Does this make sense to you guys?
Yeah.
Okay, so then in this case, after that, it's pure algebra. You see how what I was saying earlier, that we don't have to do the complicated 3D integral. We're going to end up with basically a simple one-line integral. Okay, instead of having triple integrals or doing integral that is with respect to x and y and z, it's going to be with respect to r, in this case, the radial direction. So here is the integral then we're going to find. The work in this case is going to be equal to, again, 1/4 pi epsilon naught times the product of the two charges, which is q naught. And the integral now is still from infinity down to r vector. And I'm left with dr over r squared with a negative sign. Okay. And here is something that you probably have done enough of it in calc, which is, what is the integral of -1 over r squared? When I'm in sharing my screen, I can't see the chat, so you guys probably, that's why I sometimes have to. So what is the integral of -1 over r squared from your calc classes? This should be calc 2 or calc 1 or something, no? Any idea? What is the antiderivative of 1 over r squared with a negative sign of it? Which function, if I take its derivatives, gives me -1 over r squared? Okay, 1 over r. Here is a secret about integrations. There is no rule about them. Okay? I mean, somebody will teach you and tell you, okay, we're going to learn about how to find the antiderivatives. There is no rule in finding antiderivatives. The only rule about it is remembering them or consulting references. So this is not a finding solutions to differential equations, which some of you probably will be taking or are taking, DFQs, or integrating. There is, I mean, derivatives, yes, there is that power drop, and or derivative of ln is 1 over x, so the derivative. It's when it comes to integrations, you say, okay, what is the function? If I take its derivative, I find this thing. And then you sift through the book, or you find an integral table, and you find this is the one. You test it, it works. Okay, so the only proof for it, if you wish, is to test it. So as far as he's saying in here, 1 over r, if this is basically what he's saying, if you guys take the derivative of this function, you're going to find negative 1 over r squared. Is he right or is he wrong? I need somebody else to confirm it. Okay, Rene actually confirms. Okay, for us, you pass the test. Okay, Rene already confirmed it for you. I mean, it works. Okay, if you take the derivative of 1 over r, it should be negative 1 over r squared. So that is why you're saying in here in this case, if somebody else tells you otherwise, that there is a rule for finding integrals, I think they are not telling you the truth. Okay. The only test for it usually is to actually do the derivative to test it, and if it works, it works. Okay, so in this case it is, but it's just so simple integral that people are, they can actually make it some sort of a rule. Okay, so the work in this case is equal to that's not actually a rule. Actually, it's a kind of a, how about secant of x squared minus 1 over x. Find the derivative. You have to bring it to, I mean, you see what Faraz is saying in here? It gave us some sort of a formula for it. What I'm saying in here, if I give you a function that involves all the things, usually what you do to integrals, you try to bring them to a form so that you can do this thing. Okay? So you do change a variable, you plan this, you change the boundaries, you do things, and at the end you say, aha, this looks familiar. This, if I take its derivative, it's this one. So you rework your magic back to where you started from. That's the only thing you can do in when it comes to integration, is make a change of variable to bring it or use the chain rule or whatever. Not chain rule, I'm sorry, the integration by parts or something to bring it to a form that you look familiar. Okay, basically that's what it is. Okay. Okay, so I'm not discounting this rule for us so that you know, okay? But what I'm saying in here is that in general, this is basically what you say, okay? You bring it to a form that is, okay. So am I still sharing the screen? Yes, I think so. Okay. So then the negative is consumed in the antiderivative. Okay. The negative is consumed in the antiderivative, and the answer is 1 over r. And basically the question then in this case is 1 over 4 pi epsilon naught times the product of the charge q naught divided by r, evaluated between infinity and 0. I mean infinity and r, I'm sorry. Infinity and the vector r. The vector r, all we need for it is a number. It's the distance. Okay? And at infinity, when r goes to infinity, we said that there is no interactions, so assume there is no potential energy there. And if you guys remember from physics 4a, potential energy is defined within a constant, actually. What matters in this case is actually the difference in potential. The same thing is holding true in here in this case too, because what we actually did is find the work, and the work in this case is the difference in potential. The difference between the potential at infinity, which I'm going to assume to be 0, and the potential at the position r, which is going to be this value. So the potential energy in this case is going to be defined as 1 over 4 pi epsilon naught times q naught divided by r, whereas the potential energy is taken at infinity to be 0. Okay? So this is the potential at a distance r. Okay? So the purpose of this exercise then is to show that we actually have found the work, and it's independent of the path. It depends only on the final and the initial position. It depends on infinity and position where we are right now r. Doesn't depend which way you actually come through it, because this integral, as a matter of fact, if somebody says, okay, how about if we don't come through a straight line? What happened? Well, in this case, look, you're going to come through a different path. It doesn't matter. So you come through this path. Okay, at some point, you're going to travel radially, in which case the dot product resolves to this number, negative dr. And at some point, you're moving in a horizontal, I mean, in an azimuthal direction, in the d phi direction, and the, or I'm sorry, control. In the phi direction, parallel to the, I mean, going on some sort of a circle, and at that point, that dot product gives you 0. R hat times phi hat is 0. So if your path takes you on some sort of a zigzag pattern, it doesn't matter. The only thing that is going to survive is the radial displacement only. Because dl, somebody might say, okay, what happens if dl is actually made up of two displacement? dr in the radial direction plus some r d theta in the theta hat direction or phi hat direction. So in this case, this gives you 0 times r hat, so it doesn't matter how much angle you move, okay? So the only thing that is going to survive is the dr, the displacement coming closer to the charge, okay? So this work is really independent of how you get from infinity toward the charge, toward the distance r from the charge. So this work doesn't depend on the path. Therefore, it's a conservative force. So this electrostatic force that we've been dealing with is an electrostatic force, and the potential is this much between two charges that I have just defined is this value. So this is the potential energy. Potential energy. The unit for the potential energy is the same unit for the kinetic energy, is the same unit for energy whatsoever, which is the joule, okay? Contrast that one with another energy, with another expression that we've been looking at, namely the force. The force was equal to Q times E, okay? Or Q naught times E, because the E was created by Q. The E was created by Q itself, and we brought a charge from infinity, which is Q naught. So the Q naught was subject to this force. So that's how much Q naught was subject to. So this is the force, and this guy is in Newton. That's a force. The other one is an energy. An energy is a scalar, is a number. It's not a vector. It doesn't have direction, which is just a number. R is just the distance. It's 1 over R. So in this case, it's actually a joule. So as we have defined the electric field to being basically the ratio of the force over Q naught, we're going to define the potential, the electrical potential, as just being basically, so that this expression now can be written as Q naught times V. So a charge Q creates an electric field at a distance r from it, which is given by 1 over r squared times the r hat times the charge itself divided by 4 pi epsilon naught. But also in that point itself, there is what is called the potential. If I put a charge in there, that is going to be subject to this potential energy. So this is the electrostatic potential. So it's a definition for it is the same thing without this Q naught, without this external charge Q naught. So the potential now, V is equal for a charge. This is for a point charge. All of this discussion for a point charge, 4 pi epsilon naught times Q over the distance. That's it. So that is how the potential is. Now, if you bring a charge Q naught, it's going to be subject to an electric field, electrostatic force, which is equal to the charge times the electric field. And also there is an energy there for it being there, which is equal to that charge Q naught times V. This is a new concept now, which is the electric field. I mean, the potential field, the electric potential, okay? So this is V, so this is my electric potential. This is similar to the electric field, how I defined it in relationship to the charge, but this one is defined into how it's related to the electrostatic energy, okay? So the same thing as saying force equals to the charge times E, we're saying the energy itself, U, is equal to Q naught times V, where V is the potential, okay? Now, before we move any further in here, there is a very important point I need to relate this to. So the force derives from a potential. We write it as equal to, again, in 1D, it's minus the derivative. In more than 1D, we're going to write the force, actually, first of all, in its components. Remember, there is a Z component that I'm not writing. That each component, it's its own corresponding derivative. So fx is minus the derivative of u with respect to x, and fy is the partial derivative of u with respect to y. So this force F derives off of u. It comes from u, basically, where symbolically we write this expression. So this is the right thing to write it. So this is what we really should have in mind the derivative with respect to x with a negative sign is my x component of the force. The y component of the force is the negative of the derivative with respect to y of the potential, the potential energy, and the z component, which I'm not writing, is the negative of the derivative of the potential energy with respect to z. So this is what it means. Symbolically, we represent this same thing as saying the force itself, F, is equal to minus grad of u. Okay, that is the same thing. Where the grad now is an operator. It's the derivative operator, but it's in space basically, where the grad is just looks like a vector, which I take the derivative with respect to x in the I hat direction, plus the derivative of with respect to y in the j hat direction, plus the derivative with respect to z in the k hat direction. Now note the following: u is a scalar, u is a number. So I have to plug the u here, and I have to plug the u there. But it's a multivariable function. Okay, it depends on the position x and y, okay, and z in general. So this is what this thing does. So if you operate u on a scalar, you bring it and you take its derivative with respect to x in here, and you take its derivative with respect to y in here, and that is what that operator does. Take a negative sign, again, the cosmetics in here, we need the negative sign just so that we say potential plus kinetic equal to a constant. That is basically what the total mechanical energy of the system is. So this is how the force works. Similarly, in the same fashion, the potential and the electric field, because the difference between them is just Q naught. So the electric field derives of a potential in a similar fashion. Whereas the force was on one side, now it's the electric field. Whereas the potential energy was on the other side, now it's actually the electrical potential. So this is how these two are related to one another. The same operator, which is the gradient in this case, this is what this thing is called, gradient, that's the same thing applied. So in this case, V is the scalar, the potential, the electrical potential is the scalar. I know it's a dry, and this is one of the classes when I teach that a lot of people hate the most because it's dry. I promise that when we do math, problems, it's a lot easier than this, but at least I need to get those concepts through. And this is one of the things that it's kind of a lot more math than physics, actually. And sometimes it's kind of you have to remember things, especially for those who did not really have partial derivatives. It's kind of too many things at once. So I apologize for that, but there is no way out of this. I'm sorry. I mean, even the book itself has these things. I mean, any textbook, actually, you open it, once you reach the potential, you have these partial derivatives that are thrown all over with complete disregard to the fact that some of you probably have never seen them before. So what I'm saying in here is, first of all, you have had practice on them. Don't be stuck on the symbols, okay? Just look at them. When we're doing them, they're going to be a lot easier. Just like when we did this integral, as a matter of fact, it was a single variable integral. So we didn't end up with the 3 variables and do all of this in 3D or anything like that. Even this dot, and the reason why that is because this dot product made it so, okay? The dot product made it that only we have one integration to do, because the theta hat with the dot product gives me 0. Because the radial displacement is perpendicular to the angular displacement, therefore I am done with that, okay? So this is basically, at this point, this is the definition of the potential for a single particle. Now you ask, how about if I have more than a particle? If I have a multitude of particles. Then in this case, we go back to our old friend, our BFF. Does anybody remember our best friend in here forever? If I have more than one charge, do you guys remember what's its name? What did we say we invoke? This is the question for the day, by the way. This is what you need to answer to tell me, what do you need to invoke when you're dealing with more than a charge? I'm calling it BFF. What we should invoke for more than one charge. So basically, here is the question. We did all of this discussion just for a single charge. Now, I want to bring another charge to the mixed. Okay, very good. So that is the answer. we need to invoke the superposition principle. So that is the answer to today's question for the discussion afterwards. For more than one charge, since we did all of this discussion for a single charge, how can we handle it for more than a charge? Well, we treat that, those many charges to, let's take two, for example, find the potential for one, find the potential for the other, and add them up, okay? Why? Because it works. That's the superposition principle. You guys understand the answer to the question today? Yes? Okay, yeah. Very good. So the question today is, what should we do when we have more than a single charge? And it was true for the electric field. It's true here too. We invoke the superposition principle. So doing that without having to go through the whole process all over again, basically we can define the electric potential energy in this case as follows. If I have more than a charge, I have a bunch of charges and they are interacting. So the electrostatic energy in this case, I'm bringing more than one charge to put it next to my charge. So I bring one, now I have two. Then I bring a third one. It's going to, I have to build energy against one and the second. Now I bring a fourth one, I bring a fifth one. So the potential energy is going to be 1/2. And I will tell you why that 1/2 is, because you're going to count the charge twice, okay? Times 1/4 pi epsilon naught times the sum over, oops, what happened to my symbol? The sum over I hat, j hat, those are not the, or let's call them M and M, Mn. M and N, okay? I'm counting the charges now, okay? Of Qm, Qn divided by the distance between M and N, with the condition that M is not equal to N. Okay, so I multiply Q1 times Q2 and then divide by their distance. Then take the Q1 times Q3 and divide by distance. Take Q2 and Q3 and divide by its distance. Take Q1 and Q4 and divide by its, you see the process? But if I do it this way, I will repeat. I will do Q1 and Q2, but at some point when I'm doing Q2, I'll do Q1 back again. Hence this factor of 1/2, that's all. So the factor of 1/2 in this formula is to avoid double counting, that's all. Because, but make sure you're not doing the potential of the charge with itself, because that distance will be 0. So you're going to divide by infinity, by 0, which is infinite. So the sum in here between all the charges paired together, okay? So you assemble them, many of them, put them together one next to one another, and that's basically how you find the electrostatic, in this case, energy. Okay, so this is in joules. So this is how much you assemble them. In symbol formula, symbolically, if you have a distribution of charge, let's say, for example, if I have a blob of charge in here, and I'm interested in finding the potential in somewhere else, the electrostatic potential. And this charge in here is some dq, which is some distribution of charge. So I find the charge dq, this is the distance r, and or r, in this case, r hat, or r prime, and then I integrate through the entire distribution, okay? Okay, so that's basically how this thing is. So from this point on, we're going to be summing using the superposition principle. So this sigma then becomes just the integral. This is the potential. I'm sorry, there is a difference between these two. This is energy, and this is actually potential. In other words, I don't really have a charge in here. I just have points in space. So let's do an example in here. I know we have about how much? 25 minutes left. Okay. Let's do an example in here, and we're going to cite, and I think it's one of the problems that you have in there in the book. So, and it's also 12 nanocoulombs and 12 nanocoulombs. One of them is negative Q, and one of them is positive Q. And remember that problem that we did when we did the chapter 21, trying to find the electrostatic field. And I said that you can find it, and the book said to find it somewhere in the middle, and somewhere in here, not necessarily in the middle, but in here it's going to be in the middle. Here is the problem. We're going to find it anywhere. we're going to find, first of all, the potential energy, the electrostatic potential, and then we're going to find the electric field. So we're going to take a point in space. We're going to take this one as the origin of the x-axis. This distance, for simplicity's case, I'm going to call it d. Okay, and this distance is going to be negative d. Okay, so in my dipole, in this case, it's 2d. If I don't do 2d, what happens is I will be carrying 4 with me all over. I mean 2 squared everywhere. So I'm going to make it easier and make the distance of the dipole to be 2d. Okay, so that 2 divided by 2 is going to be 1, so that I don't have to carry that extra term. Okay, but remember the dipole moment P in this case is not Q times the distance, it's Q times the distance, but the distance now is 2d. So it's Q times 2d. That is the actual dipole moment in this case. So I'm going to go in point in space, it doesn't matter which, and I'm going to find the potential in that point. This charge, which is negative q, is situated at a vector distance r negative. The charge at a positive, which is, I'm assuming that this is the positive, is situated at r positive. The point in space is r. The distance is d in here. So I want to find the potential everywhere in space. And empowered with this expression, once I find v, I should be able to find e everywhere. Something that we couldn't do earlier when we were doing the electric field. So now we have a technique to finding E than we did not before, than that we couldn't do before. Even with Gauss's law, we cannot really find the electric field in here because the Gauss's law requires symmetry, and this is really not a symmetrical problem. Gauss's law can be used probably for a single charge in here. So this is actually a far more powerful technique to finding the electric field if we can find the potential, the electrical potential. So this is what we're going to do. The potential in this case, using the superposition that we just said that it's important for us, is equal to, this is the total, is V plus V minus. The potential due to the positive charge plus the potential due to the negative charge. And it's a number. That's why it's easier to handle actually than the electric field, because it's a number. And numbers, you don't have to worry about the direction. So if it's a number, it's a number there. It's not going to matter which way you're pointing. It's like the temperature, for example. If 82 degree Fahrenheit, it's 82 degree Fahrenheit, whichever way you look. Okay? So V plus is 1 over 4 pi epsilon naught times Q divided by this distance, R plus, and V minus, which is just 1 over 4 pi epsilon naught divided times this distance, and that's the end of it. That's all there is to it. So basically, the potential in this case is going to be equal to 1 over 4 pi epsilon naught times Q, which I'm going to take as a common factor, times 1 over R plus minus 1 over R minus. Okay? Where that is only the difference, the inverse of the difference of the distances, if you wish. Okay? 1 over R plus is, now I need to express these vectors now. This is in the x-axis. Okay, the I hat. This distance is d I hat. R plus is this distance. You can clearly see from this geometry that R itself, which is the position of when I want to find the electric field, is the sum of d times I hat plus R plus as a vector. So I need to take it back. Same thing. This distance, which is also d in this direction, it's d times I hat plus R now is equal to R minus. So I need to take advantage of this geometry, and that is when we solve problems, we have to use geometry. But these are vectors. So from the geometry up there, we see that R itself is equal to d I hat plus R plus. And from the geometry, actually, that we see that R minus is equal to d I hat plus R. Okay? And R can be expressed now in terms of polar coordinates if you choose to, or we make a simpler simplification. So what I'm going to do is, I know we still have about, I want to finish a little early for you guys, but what I'm going to do is I'm going to finish the calculation because it's algebra at this point, okay? I'm I'm going to finish the calculation and give it to you, post it on Canvas for you guys to see it. It involves basically, because you need to find the distance, and the distance in this case is the square root of the vector squared, okay? So you're going to square this one in here to find the R plus. R plus in this case will be R minus DI, and already R minus is R plus DI. And then from there, you're going to basically find the difference between them and find the potential everywhere. And then we should be able to find the electric field everywhere, something we cannot do in the electric field in the previous case. So here is the thing. I'm going to again continue the algebra because it's a long and tedious, honestly, and there is not much. So let me summarize basically how this is going to be done if you're curious trying to finish it on your own. So we already find R minus from this expression. R minus is clearly the sum. Let me draw it with a different vector. So this is R minus, and this is DI, and this is R. So R minus is clearly the sum of these two. R plus, though, it's this vector, and it's D times I hat plus R plus is actually R. So R plus then is actually the difference of the two vectors, not the sum. So in a similar fashion, R plus as a vector will be R. This is because this is R plus, so it's R minus DI. Okay. Now, empowered with these two expressions, we're going to use the dot product to find their squares and take their square roots to find the distance. Okay, this is something that you probably have practiced a lot in physics 4A, or you did it when you did vectors somewhere else. So you find the R's, you find basically the R plus and the R minus as quantities, as scalars, as distances, and you plug them in this expression and you work out your algebra. Basically, you find the common denominator and you find the numerator divided by the denominator expressed in terms of D and R. Okay, because you need them in D and R. D is a property of the dipole. And R is the point where you actually want to find the electric field, not necessarily in specific privileged places like in between the charges or on the same line of the charges or the axis of symmetry. Anywhere anywhere in space, actually. Once you find the potential, then you're going to find the electric field. The reason why this example is important is because we're going to do a lab on it, and we're going to find actually the potential, and from it we're going to find the electric field. There is two key concepts before we call it a day. The first one is the units. I did not mention a single thing on them, and they're important, of course. And the other one is the equipotentials. The units, first of all. Again, it should be easy from the definition of the electric field. The energy, the potential energy, is equal to the charge Q naught times V. So the unit for the potential, the electric potential, is the unit for the energy, which is joule per coulomb. But in honor for Mr. Volta, who did a lot of things, work for us in here and invented the batteries and all of that, we call this one volt, actually. So this is the unit that you hear often about. 120 volts in your household. This is the voltage, and this term in here we're gonna be dealing with from this point on. So the unit for the potential, electric potential, is the volt. As a matter of fact, it's so much important that we're going to have a new definition, a new, if you wish, unit for the electric field. We've been using Newton over Coulomb up to this point because we were relying on this definition of the units for E, which is the units of force divided by Coulomb, by the unit of charge, which is Coulomb. So E, we defined it up to this point, Newton per Coulomb. We're going to be using a new unit now for the electric field, which is equivalent, but in terms of the volt, because the volt is actually a more commonly used term than this unit. So again, the potential in this case, which is the antiderivative, which is the integral, if you wish, with a minus sign of EDL. Okay, and the unit of the voltage, or the unit of the potential, I just said it's the volt. And the unit of the electric field is the unit of the electric field, and the unit of the displacement is in meters. So from this point on, the unit for the electric field is going to be, instead of a Newton per coulomb, is going to be voltage per meter. So if you see in the homework problems, the unit for the electric field, that all of a sudden it changed, it's no longer Newton per coulomb, it's actually because of the new introduction of this concept, which is the electric field. That's why now we have a new unit for the electric field. If you don't feel comfortable or you don't like it, go back to Newton per coulomb. They're equivalent, they're the same thing. But you will find in the references in the books and everywhere else, the unit for the electric field is actually commonly used to be volt per meter, and it's the same thing as a Newton per coulomb, because if you multiply this guy by a coulomb, that is going to be a joule, and if you multiply this one, so it's going to be a coulomb in here, so this is a joule divided by meter, and a joule divided by meter, remember the force times displacement is the joule, so joule divided by meter is actually force. So this guy is in Newton. This is, of course, you multiplied it, so it's gone. So you can go back to one, but it's always in here. We're going to be referring to it as a volt per meter. That's one thing. That's important. The other thing also is the equipotential. Equipotential is an area where the potential is the same. So equi means the same potential. We are interested in the surfaces. When we do the experiment actually with the probe, you're going to be looking at the potential. Let's say, for example, you found 5 volts, okay? You're going to find with the probe, look for another point that has the same potential, which is 5 volts. So if you look in here, for example, it's 4.5 volts. If you look there, it's 5.5 volts. So you know the point between them is where the 5 volt exists. You draw the line around it, and that is your equipotential surface. So you found the equipotential. So it's very easy to do in the laboratory to find the equipotential, because you have a probes that the multimeter device, which measures, among other things, the voltages. So you can find the potential everywhere, and that potential, you can tune your location to the same potential, okay? So that's what we call equipotential. So what equipotential means is dV is equal to 0. Remember this expression that I was looking at? So I'm going to go to 2 points in space, delta V, the difference between 2 points, VA minus VB. And that is equal to minus the integral between A and B of E times DL. Okay? So this is basically the work. Okay? Remember, I have a minus sign everywhere in here. Okay? So in this case, this is the potential that I have. If these 2 points are in the same potential, that is what the definition of the equipotential is. The difference between them is 0. Okay? So on an equipotential surface, this integral vanishes, provided both A and B are on the same potential. Then, of course, this is going to be 0. Okay? If the 2 points A and B have the same potential, then this is 0. This is what the equipotential surface means. Now, if I look everywhere on that surface and find the difference is 0, that is what the definition of that equipotential means. Which means the following: since the points are the same, can be any points on a surface, that this product actually has to be 0. Since the boundaries of integration can be any points on the surface, then the integrand must be 0. It's not just because we happen to be on 2 specific points in space, like, for example, this curve, like somebody going on a roller coaster, for example. This has the same potential as this one, but of course, in this case, doesn't mean that the function in here is the same function. As a matter of fact, you can think of so many things where functions have the same value in these 2 different points. So the integrand can be different. But in this case, actually, any arbitrary points on an equipotential must satisfy this thing. So A and B becomes any points on that surface. Therefore, the integrand must be 0, which means that EDL is 0. When EDL is 0, the electric field is either 0, or the displacement is 0, or they are perpendicular to one another. Since I'm not going to take the case where E, because that's a trivial case when there is no electric field, of course it's an equipotential. So when E is equal to 0, the integral of 0 is a constant. That means the potential is constant. So E is equal to 0 is a trivial solution for this thing. That means the voltage is constant. That's true. But what if E is not equal to 0? There is actually finite value for the electric field. That is the case that is interesting. Then in this case, the electric field, because dl is actually displacement on the surface, so the displacement on the surface and the electric field must be perpendicular. So E is perpendicular to the points on the surface. So if I find this surface, for example, as an equipotential, then the electric field everywhere on the equipotential must be perpendicular to it. That is a very, very important consequence, that the electric field is perpendicular to the equipotential surface. And this provides a powerful tool for finding the electric field if we can do the lab. If we're actually sitting, I mean, if we go and meet together, you will have, for example, distribution of charges through pins. Basically, you put charges on them, you connect them to power supplies, and then with the multimeter, you go around one of the charges and find the same potential. Let's say, for example, we have 12-volt battery. So 12 volts. One of them is going to be sitting at 12 volts, the other one is going to be sitting at 0 volts, because you're going to connect the ground to one of them, that's 0 volts, and you're going to connect the positive node to the other one, so it's going to be sitting at 12 volts. If you move away from it and you go with the multimeter, for example, you find 11 volts. You move a little bit to the other side, on the same side of that point where you found the 11 point, and you will find 11.2 volt. So you need to move back. And you find, for example, 10.3. So you need to move forward until you find the 11 volts. So you have 1 point now from before, and now you have a new point. And then you, with the same method, try to find the 11 volt. And you find so many points, 11 volts. So you have found now the 11 volt equipotential. You move further now, closer to the 0 volt, where the ground is connected, and you find, for example, the 10 volt similar way. Now we have found the 10 volt, and you continue moving until you find the midpoint between 12 and 0, which is 6 volts. That should be a straight line. Okay. Now, so this is basically, let me draw the graph. Basically, how this is. So this is pin 1. Remember, I'm taking an example of 12 volts. Okay. This is where the 12 volt is connected. This is where the ground is connected. So this is 0 volt. Okay. So you went around it and you found this point, for example, 11 volts. You moved around and you found another 11 point in here. You move this way and it's less. You move this way and it's more. So same thing. Now you connect this point. This is your 11 volt area. You go around in here and you find the 10 volt, for example, to look like this. You find, for example, the 9 volt. You find so, and then you find the 6 volts, which is going to be a straight line. Okay. Then you start to go and find 5 volts, 4 volts, 3 volts, 2 volts, and 1 volt somewhere in here. And actually, they're going to be connecting in here. At some point, they will be too wide open. Now, these are your equipotentials. They are not the electric field. So the electric field, then, to draw it, it's going to be perpendicular using this basically result. So you go into the perpendicular to the surface, for example, and you draw the electric field in there. You move on the same line and you draw the perpendicular. You draw the perpendicular until you basically find yourself pointing in here. So this is the field line. This is one field line. You go this way, for example, and you find another field line pointing this way. You go straight out, you find this field, this line. You find that this way, okay? And you move this way, it's going to go in here, perpendicular until you run out of space, and then it starts to appear from the other side. So that's how the electric field lines would look like. So you have found the electric field using the electric potential. This is how the lab works, actually, if we're doing it face-to-face. You go with the multimeter, you find your equipotential surfaces. Once you find your equipotential surfaces, you use that to draw your electric field. That is, if you have a point charge on one side and if you have point charge on the other. In another configuration, what you do actually, you do the same fashion in here. For example, you draw, these are called conducting basically pens. You draw a conducting pen in here and a point, and again, the equipotential surface in here. But the equipotential in here is going to really be weird in here. But again, you're going to connect them, and that is how it's going to come this way. Okay. And provided you connected the positive in here, and then the ground here, the node, the negative side in here, and if you did the plates, 2 lines, you're going to find straight out. All of this is we're going to 11 volt. This is 10 volts, and so on and so forth, until you reach the 1 volt. Okay, and the lines would look like this. If you take measurement in here, you're going to find 0 volts. In here, it's 0 volts, indicating that the electric field actually should be, no, I'm sorry. Forgot what the result in here. Anyway, the electric field will be 0 in here. Okay, because this would behave like parallel plates. Okay, I'll try to remember the exact math for it to give you the. This is basically how the lab would have worked if we did the lab using the electric field. Here is, in a nutshell, what this chapter is all about. Again, we're using the concept of the electric field to, the concept of the electric potential to find the electric field. That is the whole purpose of it. Another way of finding the electric field, if you wish, in addition to the 2 techniques we have learned so far, which is the direct integration to find the electric field, which is actually, it's a little bit cumbersome because of the fact we're dealing with vectors, that's all. And we have to take directions into account. Then we found Gauss's law. Gauss's law was really a taking advantage of the symmetry in the problem. And then we found this one in here, which is now similar to chapter 21, with the exception that you're not dealing with vectors. So when we do the electric potential, which somebody needs to remind me, if you guys don't see it by tomorrow, please send me a reminder saying that, hey, what happened to the dipole? We need to see the calculation for it. By the way, and we still have about less than 5 minutes, okay, to finish this. I already promised you a solution for those 2 problems, and I posted them for you guys. So hopefully you guys have no questions about that. When we meet on Monday, we're going to have probably no more than maybe half an hour finishing this chapter, because we need to do some problems from this chapter, which we didn't do much, okay? And then the remainder of the discussion will be on the exam. The exam is going to be on Wednesday, okay? And then we will meet after that for the lab session, focused completely solely on the exam, okay? We're going to do problems, we're going to discuss them. I already assigned homework for chapters 21, 22, and 23. They are actually on Canvas for the paper version of the homework, the one that you turn in on Canvas, with the solutions requiring the 6 steps, and every step is graded, as you can see from the rubric. And also, the homework is also available on Mastering Physics. Some of you are into a problem when registering for this class because it basically the deadline for the registration has expired. So I added extra time for you guys to register for that class on the on Mastering Physics. And also I extended the homework assignments on that. Now, before we go and I start asking me the practice problems for the final, it is all of your homework assignments. So far we have 3 homework assignments. Each homework assignment has 5 questions. So you have 15 problems already of assignments. In addition to that, you have the 2 problems that are part of the extra things. So those are your 17 problems to look at, understand, know from top to bottom how to do problems for the written part of the exam, which is on Wednesday the 16th, okay? When we meet on Monday, I need you guys to be comfortable with them, ask questions about them, we do them, we go through them, okay? So that you guys have no surprises. Now, there is another version also that you guys have on Canvas, and that is the quiz, okay? That is actually to also incite you and prepare you for the concepts too. And that is due on Monday though, because past Monday, I really want you to be 100% fully concentrated on the exam itself, doing all of those problems, understanding them from top to bottom, understanding what it takes from them. So you have to understand how to find the electric field using the integrals for different distribution charges. You need to understand how to use Gauss's law for different symmetries, and you need to understand how to find the electric potential also following the problems. Problem 83 from this homework assignment is a nice problem. And problem 82, I think, or is it 82 and 83? I don't remember. Let me check quickly in here. Assignment homework. From chapter 23. Yeah, I think both 82 and 83 are nice problems, so you really need to have full understanding of them. One of them is basically what is used in nuclear physics. So you have a what is it? The atom of Le Plomb. What is lead? Yeah, and then you hit it with an alpha particle, depending on the angle with which it comes. I think problem 74 is the one that connects to it, comes heads on. So in this case, it's going to come from infinity and you want it to stop. But usually it comes at an angle. That's what problem 82 or 83, I don't remember which one, does. It comes at an angle and basically deviates. So at this point, there is an angular momentum and there is conservation of angular momentum as it comes in with that. Okay. So those are the homework problems. I really need you to have full understanding of what these problems are, knowing them. Come exam time, you will have the period, which is an hour and a half, plus another hour you'll be given to make sure you fix all of the issues with uploading and things like that. So you did your homework, I mean, you did your exam, you finished all of the solutions, you did everything. I don't think you will have time to communicate with anybody else or look up into Google or anything else, because you're not going to have time to do that. So utilize all of your time to do your own exam and then upload it. Make sure you review it before you upload it, and then upload it and be done with it. Okay, so that's basically how much time you will be allotted for the exam on Wednesday, December 16th. So if you're working on that time, please take at least the 2 hours and a half off so that you do your exam, and then you can go back to work or do whatever you need to do. Okay? Any questions? No? Don't forget the question of the day today, that you're going to go to the forum and put the answer to it. You guys remember it. No questions? You don't have any questions? We're 1 minute past the time. See you guys on Monday.